Welcome to the chapter Heat. This slide presents the overview of the chapter. Take two bowls, one filled with hot water and the other with cold water. Gently sprinkle some food color in both the bowls. Observe the motion of small grains of food color. We notice that the grains of food color exhibit jiggling movement, that is, they move randomly. This is the result of the random motion of the molecules of water in both the bowls. We also observe that the grains of food color have more jiggling movement in hot water than those in cold water. We know that every moving body has some kinetic energy. As the particles, that is, the grains of food color in both the bowls move with different speed, are said to have different kinetic energies. Finally, we can conclude that the molecules or particles of the hotter body have comparatively larger average kinetic energy than the colder body. In this way, the average kinetic energy of molecules of a body is indicated by the temperature of that body. In other words, the average kinetic energy of the molecules is directly proportional to the absolute temperature. Let us do another activity to learn more about the relationship between temperature and kinetic energy. Take a jar half filled with water and heat it to 60 degrees Celsius. Take a cylindrical glass jar which is transparent and fill half of it with hot water. Now pour some coconut oil over the surface of the water very gently, such that the water and oil do not mix. Close the jar with a lid containing two holes. Take two thermometers and insert them into the jar through the holes in the lid. Put the thermometers in such a way that bulb of one of the thermometer is inside the water and the other touches only the coconut oil. Now note the readings of both the thermometers. The mercury level in the thermometer kept in water falls, while the reading of the thermometer kept in oil increases. It is because the average kinetic energy of the molecules of oil increases, while the average kinetic energy of the molecules of water decreases. In other words, the temperature of oil increases while the temperature of water decreases. Some heat energy flows from water to oil. As a result, the kinetic energy of the water molecules drops and the kinetic energy of the oil molecules increases. In this way, water loses energy while oil gains energy due to the temperature difference between them. From the activities 2, 3 and 4, we learn the following differences about heat and temperature. Heat is the energy that flows and temperature is the quantity which decides the direction in which heat energy flows. After learning this, let us now learn how these quantities are associated with a system through the concept of specific heat. Let us do a lab activity for determination of specific heat of a solid. Click each tab to know more. The aim of this lab activity is to determine the specific heat of a given solid. Materials required are calorimeter, thermometer, stirrer, water, steam heater, wooden box and lead shots. Let us follow the procedure. Determine the mass of the calorimeter along with stirrer. Note down the mass of the calorimeter. Now fill the water to 1/3 of the calorimeter. Measure the mass of the calorimeter along with water and note down the same. Place the calorimeter in the wooden box. Measure the temperature using thermometer. Take a few lead shots. Put them in steam heater or hot water. Heat them till the temperature reaches 100 degrees Celsius. Quickly transfer the lead shots into the calorimeter with minimum loss of heat. Observe that the mixture settles at certain temperature after some time. Now measure this temperature and also the mass of the calorimeter along with the contents, water and lead shots. Observations. Mass of the calorimeter and stirrer is equal to M1. Mass of the calorimeter, stirrer and water is equal to M2. Mass of the water, M, is equal to M2 minus M1. Temperature of the water in calorimeter is equal to T1. Temperature to which the lead shots are heated is equal to T2 is equal to 100 degrees Celsius. Temperature of the mixture is equal to T3. Mass of the mixture is equal to M3. Mass of the lead shots is equal to M3 minus M2. Specific heat of water is equal to SW. Specific heat of calorimeter is equal to SC. Inference. As the heat lost to the surroundings is zero, we can state that the heat lost by the solid, lead shots, is transferred to the calorimeter and water for obtaining final temperature. Let the specific heat of the calorimeter, lead shots, solid, and water be SC, SL, and SW respectively. According to the method of mixture, we know that heat lost by the solid is equal to heat gained by the calorimeter plus heat gained by the water. M3 minus M1 into SL into T2 minus T3 is equal to M1 SC into T3 minus T1 plus M2 minus M1 into SW into T3 minus T1. SL is equal to M1 SC plus M2 minus M1 into SW into T3 minus T1 by M3 minus M1 into T2 minus T3. Finally, we can calculate the specific heat of the solid lead shots using the above expression. Let us perform an activity for evaporation. Take a small amount of spirit in a cup. Pour a few drops on your palm. Your palm feels coldness. Let us see why this happens. Once again, take a few drops of spirit, say 1 ml, and pour the drops into 2 petri dishes individually. Generally, the petri dishes are shallow glass or plastic cylindrical lidded dishes used in the laboratory. Place both of the dishes under a ceiling fan. Close one of the dish with the lid. After 5 minutes, check the quantity of spirit in both dishes. We observe that spirit disappears in the dish, which is kept open under the ceiling fan. At the same time, some quantity of spirit can be found in the dish which is closed. Similar observations can be noted for the water drying up on the floor and in wet cloths under a ceiling fan. In all the above cases, the state of the liquid changes to vapor. This change in state of any liquid to vapor is called evaporation. Let us learn more about the process of evaporation to understand the reasons behind the above observations. The molecules of spirit continuously move with random speed in various directions when the spirit is kept in the closed dish. During their motion, these molecules collide with one another and transfer their energies. The molecules on the surface get enough energy to escape from the surface when they are collided with the molecules within the liquid. These molecules, after escaping from the liquid surface, collide with the air particles near the surface of the liquid. A few of them even return back to the liquid. Hence, when a liquid is exposed to air, the particles at the surface continuously escape from the surface until the entire liquid disappears. This process is called evaporation. Now, let us observe the reason for faster evaporation of spirit under the fan. In open air, the number of returning molecules is reduced to a large extent when air is blown over the surface of liquid. This is because any molecule escaping from the surface is taken away from the liquid surface, so this raises the rate of evaporation. That is why in an open pan, the spirit evaporates quickly than when it is closed. In this way, we learn that the process of evaporation is a surface phenomenon. Temperature falls during evaporation, thus making it a cooling process. As the molecules of liquid escape from the surface into the air, the process of evaporation also involves phase change. The rate of evaporation of liquid is determined by the factor like temperature, surface area of the liquid, and amount of vapor present in the surrounding air. Example: when we work, the body produces heat. This increases the temperature of the skin. As a result, water present in the sweat glands begins to evaporate. Depending on the factors of evaporation, the body becomes cool. The reverse of evaporation is technically known as condensation. Let us learn about this process in detail. Take a glass tumbler, place it on the table. Fill half of it with cold water. We know that the temperature of the cold water is lower than the temperature of the surrounding air. Air has water molecules in the form of vapor. Molecules of water in air with higher energy collide with the water molecules in the glass tumbler with lower energy. As a result, water molecules in air lose their kinetic energy. This causes a drop in the temperature, and molecules of water in air are converted into droplets continuously. Hence, the water molecule's temperature in the glass tumbler increases. This process is called condensation and is a warming process. Condensation can also be defined as the change from gas to liquid state occurring at the surface of the liquid. For example, when we complete our bath in a bathroom with hot water, the number of vapor molecules per unit volume is high when compared with the outside. When you dry yourself with a towel, the vapor molecules surrounding us condense on our skin, thus making us feel warm. Let us learn the reasons for this. Thermal equilibrium with three bodies. Now, let us learn about the thermal equilibrium with three bodies. Consider two different systems A and C in thermal contact. These systems are in thermal equilibrium individually with another system B. If system B is in thermal equilibrium with system A, then both systems have the same temperature. Likewise, system B and system C have the same temperature. So the systems A and C will also have equal temperature. In this way, the systems A, B and C exist in thermal equilibrium state with each other. After learning to measure the physical quantities, temperature and heat, let us learn about the units used to express the measurement of these physical quantities. The SI unit of heat is joule, CGS unit is calorie, CAL. The amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius is called calorie. 1 calorie is equal to 4.186 joules. The SI unit of temperature is Kelvin, K. It is also expressed in degree Celsius, C. The degree Celsius is converted to Kelvin by adding 273 to the value of temperature in degree Celsius as per the relation 0 degree Celsius is equal to 273 Kelvin. Temperature in Kelvin, K, is equal to 273 plus temperature in Celsius. Until now, we learned about temperature using larger bodies. Let us learn about temperature at molecular level through activities. The following table shows the differences between heat and temperature. Numerical problem. How much heat is needed to raise the temperature of 2 kg of copper from 20 degrees Celsius to 70 degrees Celsius? Hint: specific heat is equal to 3.9 into 10 square joules per kg degree Celsius. Click the tab to view the solution. Knowledge check. Attempt the following question to check your understanding. Knowledge check. Attempt the following question to check your understanding. Knowledge check. Attempt the following question to check your understanding. Knowledge check. Attempt the following question to check your understanding. Knowledge check. Attempt the following question to check your understanding. Knowledge check. Attempt the following question to check your understanding. Knowledge check. Attempt the following question to check your understanding. Read the questions and attempt the answers on your own. You can click Answer for your reference. Take up the following activities. Collect the information about working of geyser and prepare a report. Suggest an experiment to prove that rate of evaporation of liquids depend on their surface area and the vapor already present in the surrounding air. Evaluation. Test your understanding of the lesson by taking the mock unit test.